Okay, and here we continue along the same path on the second video for homework 1. And so this is the StatCrunch demo. We're going to make a generic scatter plot of x versus y. So graph, scatter plot. And to make things easy, x is x, y is y, group is group. Actually, I'm going to do it without grouping first. But you don't have to capture this one. I just want to show you it's a big mess. It just looks like a big mess of points. So you may say, hey, there's nothing to it, it's just a field of messy points. Okay. Now we're going to group by group, and while we're at it, we may as well overlay polynomial of order 1. That's just a line of best fit. You could have overlaid a line of best fit before, but for StatCrunch, when you ask it to split the data like that, then it will overlay a single line of best fit for each group. And remember, we discussed that exactly one of our groups had a negative correlation and the other 3 groups had a positive correlation. So we get this scatter plot. And you notice, or did I say that backwards? Let me see. It should be here. The correlations for x and y. See, my memory was wrong. U is positively correlated, so the slope should also be positively correlated. So U is blue, and indeed it has the positive slope, and the other 3 have a negative slope. So I want to try, what if I just want to see one group? I could say group equals W. I just see that one. Okay, and I could just try another one. W, V. And it'll be blue. You could change the color, but there's no need to. And U. So this could be useful because usually what happens is they're all just on top of each other, and you just may want to see behind. So if you want to peek behind those layers, then you could go right ahead and do that. Okay, so that's step 11. Now we're going to adjust the existing graph. Oh, I lied. I want both plots. I'm sorry. So I want this plot for step 12, and I want this plot for step 11. Okay. Now step 13 is just for fun, but I wanted you to see how to do that. Graph QQ plot, and just pick, you know, X or Y. I'm picking Y. Group by group. And then you can see that our group Y values are fairly normally distributed. So this is a test for normality if you do a QQ plot. Now technically a QQ plot is lining any 2 data sets up against each other to see if they're the same shape. But what we're doing in StatCrunch is a limited version of that, where your data set is lined up against a normal distribution to see whether it is normal or not. So within StatCrunch, QQ plot only means take your data, line it up against a normal distribution to see how normal your data are. Okay, so that's step 13. We don't need that. We don't need to include it. Okay, 14. Test for similarity between 2 groups of your choice. So I'm going to use 2 of the groups over here. And I'm going to use z-test and t-test. So I'm assuming that I'm trying to find out if group, let's say, W and X are similar. We already suspect they're not, because we already saw this scatter plot, which is group by group, and it looks like these guys are kind of different. And we have this evidence that the groups are different as well. Keeping in mind that these 2 groups may be similar, these 2 groups may be similar, but for example, group U and V are different, and W and X are definitely different. But let's see what the numbers say. We have a very large data set for all these groups, and so we should be getting high significance anyway. Okay, we're going to test for similarity. Z-stats, we're going to say 2 sample with data. For both, let's just put the values in X. Okay, and then we're not going to use the standard deviation, but we're going to say group equals, and it's whatever you want. Let's say group equals U. I have U and V. I could do that. Any 2 groups There you go. As long as there's two groups you have. And we're going to choose, because we're comparing group versus group, we're going to do a hypothesis test rather than a confidence interval, but either one would be fine. Right now we're actually kind of just playing around. Okay, so I'm going to keep this window open and do the same exact thing, but now for t's. Okay, so stat, t-stat, toSample with data, values in x. So it's going to be exactly the same thing. Where group is, we better use the same groups though. I don't want to pull variances. And we're going to go ahead and see that if we have a t-test and a z-test for large samples, then we're going to get very similar results. It's not going to matter at this sample size level. But if we had a small sample, we should be using a t-hypothesis test. So when in doubt, always use the t-hypothesis test, because if you're wrong, it doesn't matter. But if you use the z-hypothesis test when you're not supposed to, you could get wrong answers. Okay, so the t-hypothesis test always catches up to the z-hypothesis test eventually when you get a large enough sample size. So when in doubt, use t. All right, now you really shouldn't be using t-test or z-test to compare these groups because there's 4 of them. Actually, even if there's just 2 of them, I would just throw out z-test and t-test entirely and head right for ANOVA because it's so much more useful. So let's go stat ANOVA, and we're going to do one-way ANOVA, and you're going to select values in a single column, and let's put responses in Y, factors in group. Factors are the groups. So I don't know why they call them factors, that's what they call them. You want Tukey because without Tukey, ANOVA is kind of pathetic. It tells you whether or not something's different, but it doesn't tell you what's different. So then we hit compute, and then you get all this output. You could basically ignore this first part. So you're going to get a significant p-value. If you don't, that's okay. It's fine if your p-value is not significant. It's pretty unlikely, that's all. So what this is telling you, because the ANOVA p-value is so small, it's saying something is different, but I'm not going to tell you what. Very well then, I'm going to look at the subtracted differences and see, is U different from all of its friends? Yep, U is different from all of them because you have very small p-values for all of these comparisons. What about V subtracted from everything but U? Well, it looks like V and X are similar. So let's look at our plot. V and X are similar, and our eyeballs kind of confirm that for us. I'm kind of surprised that U and W are different, but hey, your intuition can be wrong, and so that's why we do this. But your results should not completely contradict your intuition on the matter. It should be somewhat in line. So Tukey is saying that these two, where was the similar one again? Aha, V versus X. V versus X, these two are statistically similar, and Tukey can't tell the difference. But Tukey can tell the difference between U and W, and certainly all the other groups are different. So that's what ANOVA is saying. Okay, going to step 16. It's often necessary when doing statistical work that you need to do what's called recoding variables. That means it's often necessary to rename your data for reporting purposes or to keep yourself from going completely insane. So we're just going to recode, we're going to rework T and S using this thing called compute expression. The compute expression is generally an extremely useful tool. But my expression I'm going to use is an if-else, and I'm going to use this to recode my variables. If T is 0, I want to replace the 0 with disagree. It says it's just a Boolean variable. It's going to be 0 or 1. So if T is 1, I want to say agree. I just made these up. It's not in response to anything. I'm just going to call this new T. And I'm going to just make use of this box here and say if S is equal to 0, I'm just going to say that's going to be female and male. Now sometimes it turns out that you have to put your variable names in quotes, or your responses in quotes. If you've already used, say, male somewhere else as a variable name, then you need to protect these by putting them in quotes. It's usually not necessary, but again, StatCrunch is really finicky, and also you want to be able to make use of other variables sometimes and make complex formulas. So if you want to actually protect those group names, put them in quotes, but usually you don't have to. Okay, so these are just completely bogus made up categories. I just want to show you that you can recode variables. Okay, now on to step 17. We're going to have the two variables. Instead of using t and s, let's use new t and new s. And we're going to do a chi-squared analysis. Stat tables contingency with data. Okay, so we're going to pick new t against new s, and we're going to group by group. We're going to display expected count because this will be useful to us. You can pick whatever you want generally, but just for now. And that's all we want. You probably want to use 4 little screenshots for this because this is kind of tall and skinny and obnoxious. Okay, what is this saying? So this is saying for group U, there's something highly significant. And for group V, significant, W is not significant, and X is significant. So for one of your more highly significant groups, I want you to sort of stare at it and try to figure out whether it's a positive or negative correlation. So in this case, are females more likely to agree or disagree? Or you could ask it this way, are females or males more likely to agree? So in this case, females are less likely to agree. So I'm sorry, more likely to agree than they would be by random chance. By random chance, you'd expect 83 females to agree, but we have 108. And we're more likely for males. So if this box is higher, we expect this box to be higher too. In real life data, it doesn't have to be, but in this data, it will be because of the way I constructed it. But notice males are more likely to disagree than they would be by chance. Males are less likely to agree, and females are less likely to disagree. So in this case, if we had left them as 0 and 1, as they originally were, you would say that this is a negative correlation. But we've now gotten rid of the 0s and 1s, and we've just given them categorical names, so we can't really say if it's a positive or negative correlation. So the way you would write this up in your write-up is you'd say females are more likely to agree, and males are more likely to disagree. And that's the direction of the correlation. Let's see, for group W, you would say, well, look at this p-value. This p-value is above 0.05, so we're not even going to talk about it. And X is strongly correlated, so we could talk about that one. You could say, okay, males are less likely to agree, and females are more likely to agree. But it could have just as well been the other direction. Let's try the other one. I ask you in the write-up to just talk about one of your little groups and pick one that's highly significant. Okay, we didn't do V yet. Females are less likely to agree. Aha, this one goes the other direction. Here, males are more likely to agree, and females are more likely to disagree with whatever the survey is saying. So in this case, the correlation is in the opposite direction as the other two, because in here, males are more likely to agree. So you write that up in your write-up and pick at least one group to talk about. And that is the end of homework 1. And if I can figure out how to shut off this video, that would be great.